Hello, dear audience. Thank you so much for being with me in the deep learning tutorial package. Let me at first introduce you with the course by giving you a table of content. Actually, we want to prepare for the discussion of deep learning. First, we learn the essentials, and then we enter the main topics of deep learning. First, we explain the linear classification. Then we enter the discussion of cost function. Then we will talk about optimization. Then we introduce the backpropagation algorithm, which is used to train neural networks and is used for all training algorithms. We try to check this algorithm completely and in detail. Then we enter the discussion of artificial neural networks. When we know the above content, there is nothing special about artificial neural networks and even deep learning itself that is difficult to learn, because the combination of these topics is actually the main concept of deep learning. Okay, let's talk about deep learning. At first, we want to have an introduction about image classification. During this course, we also examine the link between artificial neural networks and deep learning. Why did deep learning come up? Because there was no such issue in the computer world before. Okay, let's have the introduction. At first, we want to start with a concrete and a familiar problem, which is image classification problem. We are given a discrete set of stickers, labels actually. For example, here we have 10 tags and one object. In fact, we are given an image of an object and we want the model to recognize which of these classes this object belongs to. This is a discussion of classification. Here we are specifically talking about image classification. Our input is an image and a discrete set of labels. The input can be anything, for example a sentence, and the output can be anything as long as it is discrete. That is, in fact, we have a function of x and y here. Now, why did we start this discussion? It is very easy for us to recognize that this picture is a cat. Why do we make models and discuss about it at all? Why is this difficult for a computer? And why do we need to do this with neural networks and deep learning? Now that we are discussing this issue, have computers been able to catch up to us in this discussion of image classification? The point is that this work is difficult for the computer. Here there is a semantic gap between what we as humans receive and what the computer receives. The issue of matrices is a very complicated issue. What we see is this image, and over the years of evolution our brain has learned to process this image and understand that this is a cat. It doesn't matter if this cat is tall or short, at what angle it's standing, and what light is in the picture. But if we want to know how this problem is in the computer, we have to pay attention to many things. Here we have shown only a part of the cat's mouth in the form of a matrix, and each of these is a number between 0 and 255. Now, if you imagine that these images have dimensions of 100 multiplied in 300, each pixel has 3 dimensions. RGB stands for red, green, and blue. In this example, the computer must process 300 multiplied in 100 multiplied in 3 numbers. Each of these numbers are numbers between 0 and 255. This is also 0 and 255. You know that there are different levels of color. If the image is gray, one number is enough. But for colored images, 3 numbers are required for red, green, and blue colors. Put yourself in the place of the computer. See if complex calculations and the high-level concepts of artificial neural networks and deep learnings are necessary for processing or not. Now this problem becomes more difficult if we just change the camera angle. The same object, the same camera, the same light, the same way of standing, but only the camera angle has changed, and now these numbers are completely changed. Now, for these numbers, the computer should still be able to recognize that this is the same cat. Now, if the lighting changes, if the image is dark, all the numbers in the matrix are almost 0. And if the image is very bright, all the numbers are almost equal to 255. And we can recognize only by seeing a part of a cat, although we cannot see its body. Now the computer should recognize the same way. Whereas, for example, if the background texture and the image are similar and they have similar colors, for example, it becomes difficult because the numbers and the metrics will all be the same. Now there are different types of cats. It is true that the computer can process numbers very quickly, but these numbers may be completely diverse and different. The same problem exists in NLP, sound, etc. Now we want to design a system that determines the output for us from the input. I have written the names of the labels here for clarity, but in practice these are all numbers. For example, class 1, class 0, class 2, something like these. So we give this input matrix to the computer, and it returns the output class number to us. If we want to write a function for this in Python, it will receive something like this. It will receive the image and do some processing, which our goal here is to explain this processing. And finally, it will return the output class to us. So for example, in this example, it should return the number 3. Class 3 is the same cat. Please pay attention to the fact that in Python, indexing begins with 0. Here, class 0 corresponds with the airplane class. It doesn't matter what condition the cat was in, the lighting conditions, the angle conditions, with the camera, or for example, half of the cat was clear. Those who already have the experience of sorting arrays on the computer may say to themselves that it is a simple task, but this is not the case with artificial intelligence and data-driven approaches. Because myself, the programmer, do not know exactly how I can recognize that this picture is a cat. Or let's take another example. I can tell which friend's voice is from my friend's voice on the phone. Suppose that my phone is ringing, and I answer the phone, and at the same time that I hear the voice on the other side of the phone, I can recognize which friend of mine is talking to me just by hearing her voice, for example. Suppose that the computer always wants to do work. Suppose that the computer wants to do the same work, voice recognition, They will ask you how you know who your friend was. You can't explain. because the brain has a very complex structure and we cannot guess this procedure. What we do is a data-driven approach. That is, we collect the data the same way a person learns. We collect a number of samples from each class. This number is in the millions or more. A few are shown here with different lighting conditions and angles. We provide this to the computer, and we have no business knowing how the computer recognizes which image belongs to which class, and we do not know how it learns this recognition. We just give it the input. The function we write is here. We call this input the training set. Because you are somewhat familiar with machine learning, in supervised learning we specify the output for each input. That is, we say that this image belongs to the cat class, for example. Now we call a set of these a training set, which is a set of images and a set of labels corresponding to them. The first image and its label are characteristics. For example, these can be Python lists. Now, if you see a new image that was not a member of any of these images and was new, according to the tutorial you saw, based on this tutorial, identify which class it belongs to. We call this process the training process. Now, after training, the only thing left is prediction. Prediction in predicting the class corresponding to the new input image. This stage is also a function whose input is the same as our educational model, along with the new image and the output of the predicted class label. This is the whole thing that we want to do. First category is nearest neighbor. There is a training set called CIFAR10. There are 60,000 images in this collection. The dimensions of each image are 32 multiplied in 32, and since they are colored, the total number of pixels is 3 times more than this number. The dimensions of the images are small so that the computational load is not high. Now these pictures belong to 10 classes. Out of these 60,000, we use 50,000 as training. Now we have built the training model. We want to make sure that this model works properly or not, and now we use 10,000 to test this model. How much these ratios are and how much of the data we choose for training and how much for testing is almost a matter of taste. Regarding these 10,000, we also know which class they belong to, and we want to see if the computer recognizes correctly or not. This is the standard set. The nearest neighbor algorithm says, I know which class this image belongs to. They tell me which image is related to the car, which is related to the dog, etc. When a new image is given to me, I compare it with all the images in the training set. Let's see which one is similar to them. Here are 10 more similar images. I want to know what this input image is. Now let's see which one is the most similar among these 10, belonging to a horse, for example. In this particular example, we may make a mistake. Machine learning algorithms can make mistakes just like humans can make mistakes. For example, according to the algorithm, the first nearest neighbor is similar to class 1. Now, if we consider several similar images, for example, 10 are the most similar. Out of these 10, the computer has two predictions belonging to the horse class, 3 cars. Then the majority vote means that this new image is classified as a truck. For example, these examples may occur. This is called nearest neighbor. The generalized mode is nearest neighbor, mode of a nearest neighbor. The distance criterion is L1. We subtract like for like, peer-to-peer actually arrays. Now there are different methods. For example, let's add the arrays of the final matrix together. One method is to calculate the sum of the squares of the differences of the matrix terms. These are different forms that depend on the general work policy. Now, the smaller this number is, the greater the similarity. Now we discuss how many similar neighbors we should consider. Now, if we consider 10, for example, the result will be correct. We want to strike a balance between accuracy and speed. If this sum is 0, it means that the two images are the same. I put the corresponding Python code for implementation here. No processing is done in the training phase. It just keeps track of which class each image belongs to. In the prediction stage, we have processing. We calculate this distance simultaneously for all the data of the training set. We select the most similar class with the smallest distance and the class which the highest frequency returns the algorithm to us. Now the point is that the bigger the size of the training set, the longer the runtime and the slower the speed. But what we want is exactly the opposite. But here in nearest neighbor, no time is spent for training, but it takes a lot of time for prediction. Now this is what deep learning can do. That is, it spends a long time on training, but it minimizes the processing required for prediction. It is okay if the training time is long. Deep learning training is usually done on GPU, and the time spent on it is not important at all. But when using the algorithm, which is exactly the same as the prediction phase, the speed increases and the efficiency is interesting and positive. In general, neural networks have this feature. The point is that we cannot use nearest neighbor in image recognition because now they are all one image. Pay attention to this slide. They are all one image. This is the original image, and these are the images obtained from the original image with slight changes. If you consider matrices, the numbers change completely. The numbers and the sum of the digits of the final matrix are completely changed. And from the computer's point of view, these images are not classified as the same. So it is not suitable for this issue. So we don't use a nearest neighbor in image recognition for two reasons. One, long time for diagnosis. Two, incorrect classification of images with minor differences. So what we need are other methods. Nearest neighbor classification method can be the same model, but it is not a good model for us. Now the question arises, how much should this in nearest neighbor be? Or for example, should the first norm be used to determine the distance or the second norm? These are the distance standard actually. This is the first norm, L1, and this is the second norm, L2. It means that the numbers themselves must be added or their second power. These are usually determined by validation methods. We have cross-validation and k-fold cross-validation. In this way, we try all the situations. For example, k is equal to 1, k is equal to 2, and see which k works better for that training set. These are called hyperparameters. We determine their values with the same method of testing. In this way, we divide the data into two categories, training and testing sets. We leave the testing set aside and divide the training set into two categories again. We do the training on the first batch and get a model. Now we will test this model on the second category, which we call validation, and we will get an accuracy. We repeat this work for different cars. We will see for which car we get better results. These are usually the main problems. Now, the art of a machine learning and deep learning expert is how to adjust these hyperparameters so that he is less involved in these calculations and troubles. If we learn linear classification, we have learned the basis of artificial neural networks and deep learnings. Now, let's see what is a linear classification. And after that, we learn neural networks, and then we explain multi-line neural networks, which is the same deep learning. Let me introduce you with the table of content here. You can see the table of content. These, along with optimization, are all the basics you need to work in the deep learning domain. We proceed with a visual example to make the discussion more concrete. You yourself can generalize to sound, language translation, sentence, and etc. The computer is supposed to receive this input and finally return 10 numbers if we have 10 classes. These numbers are points. For example, with what score does each image belong to class 1, or with what score does it belong to class 2, and etc. Now you look at which is the maximum among these 10 numbers. We want to design a function inside this f that will do the same thing for us. The simplest function is the linear function. We should value these w's so that when x is a cat, the score corresponding to the cat class is maximum. The easiest thing is to use the linear function. That is, the numerical value of the input images should be multiplied by the numerical value of this w. Now the question is, where does this w come from? The simplest case is fx. W is equal to multiplication, production of this w and x. We always have this bias actually. The output of this function should be 10 numbers. In machine learning, we talk about matrices and vectors actually. X becomes a one-dimensional vector that has 3072 numbers after vectorization. So you can see that the parameters or weights size are 10 multiplied in this 3072, which is the production, the result of multiplication of 32 and 3. We have colored images here, so we need 3 pixels for every single pixel of each image. Okay. Here we also have a b, so that it is really a linear function. We have a bias for each class. So when we have 10 classes, we have 10 biases. In order to make the examples more concrete, we reduce the number of classes and dimensions. We consider the number of classes to be 3. And dimensions 4 multiplied in 4. We assume the input image is a 4-dimensional vector, which is gray actually. The lines represents the classes, actually the rows, the horizontal lines corresponds with classes, and columns or vertical lines represents features here. Here the features are pixels. Never mind where this W came from for now. Suppose a source provided us with this W. Now they give us a new photo with a specific vector which is the same W multiplied in X and added to B value. Now we got 3 numbers. These 3 numbers are the same number of classes. The order is that the first is related to the cat, which is here the negative form of 96.8. The second is the dog and the third is the sheep actually. These are the scores of the classes. We made a mistake here. Now what should we do to correct this mistake? How should the first score increase and the second and the third score decrease? How about we can change the parameters? In many places this B is attached to W as a column. From here on the question is how to determine these W's. In the beginning, we usually start with a random B and a W and gradually improve the model. For the prediction to be correct, B and W must be correct. This process of correctly determining B and W and changing their values and reaching the optimal value becomes the process of training a neural network. You might say that it is not a neural network. Why? By the way, this is exactly a neural network, a single layer neural network. Before we know how to find the W and B, now let's see what these are. How is it interpreted? Well, since we have 10 classes, how many rows should this matrix have? 10 for each we need to find a weight vector. What are the dimensions of these vectors? If the input is 3072, the vector must be also 3072. If the input is 4, it should be 4 too. So each of these 10 weights that we get can be taken as 3072. So in the C14 problem, we have 10 rows and each row has 3072 columns. So we can consider each row as a weight vector for each class. We can say that we got 10 weight vectors. Now we have to do a reshape operation, which is the opposite of the vectorization operation. At first, we had an image that contained 3 multiplied in 32 multiplied in 32 numbers. And we converted all of them into a vector of size 3072. Now we have to do the opposite and produce a matrix corresponding to an image. There is a function in Python for this, which I have discussed in the Python files. As a result, you will get something like this picture. So let's see what these weights are. This is first class weight matrix, this is second class weight matrix, this is third class weight matrix, and so on. attention to this one, horse class. Pay attention. These 10 vectors, if we convert these into vectors, the size will be 3072. These are prototypes. It means that you have obtained this vector from 50,000 training data. Now a new data comes, you want to classify it. Here you have to do multiplication. Vector coefficient means a similarity measurement. When x is multiplied into the first weight vector, that is when two intersected vectors are multiplied together, we are actually comparing their similarity. In this way, we calculate the similarity of the input with the first class by multiplying the input vector to the vector of the first weight, actually first class. Now when we multiply x by the second weight vector, we are calculating the similarity of the input with the second class, and so on. We say that these weight vectors related to each class are the prototype of that class. That is, if we consider all the images belonging to that class and calculate an average, we will have an image similar to the image corresponding to this weight vector. If you look carefully, the general scheme of, for example, a car with a cat, or a cat or a dog is clear in these weight vectors. By looking at the horse class, for example, the outline of the horse is visible. In this class, pay attention that our horse has two heads. Pay attention. One to the left, one to the right, and because there were different photos and I took the average of these. The larger the inner product of two vectors, the more similar the two vectors are. Now there is another interpretation. You can enter the geometric space. Consider two-dimensional space. You can have this line equation. We draw weight vectors into dimensional space, then we consider the input image and compare the coordinates. If the input image falls in the direction of the arrows, the same classification is done as the class corresponding to that vector. And otherwise, the class of the input image is considered something other than the class corresponding to this vector. It means that we are actually separating the data from each other. In space, we consider a separator for each class, but in the simplest problems, the data may be such that they cannot be separated by a line. Maybe you need a curve, but our function is linear. They give us a line in two-dimensional space. In the three-dimensional space, they give us a page, and in the four-dimensional space, they give us a cloud. However, it is linear and cannot create curves. What we need to do is to make this linear function more complex. It means that to take it to higher levels, for example, level 2, level 3. How do we do this? By adding layers in networks and using nonlinear functions. By combining different layers, we can create more complex functions. Let's go back to the discussion of how to get W's. As humans, we can understand qualitative concepts. Now we want to transfer the same concept to the computer. Let's say which W matrix was good and which one was not good. We want to define what the best, for example, temperature is. In the computer, To define this being the best, we have to state a general concept and say it with a number. If we can numerically compare different w's, it is easy. The cost function does that for us. We give it the matrix w. If w is not good, the cost function will produce a bad number. That is, it produces a large number that says the cost of this w is high. And on the contrary, if w is good, the cost function produces a good number. That is, it produces a small number that says the cost of this w is low. So we have function and we need to find its minimum, and here comes the issue of optimization. The cost function tells how bad it is, the less the better. Now if we can define the cost function, the rest is simple, because the optimization issue has been solved in mathematics for many years. For simplicity, we consider the three of these classes. We have a cost function called the multiclass sigma PM cost function. It has different names. It is also called a hinge function, for example, and there are also other names. It is important to understand what this formula says, and now we want to explain this formula with a specific example.